The fundamental theorem of calculus. This is the most important theorem in calculus. Let's consider the following situation. Suppose we have some function f of t on an interval from a to b, and let x be a number in between a and b. And suppose we are interested in finding the area under the curve from a to x. We could represent that area by a new function, g of x, which is equal to the integral from a to x of f of t dt. And we know we can do this because the definite integral represents the area under the curve. And like any other function, we can find function values for the function g for a given value of x. Let's take a look at an example. So here f is the function shown in the graph. And g of x is the integral from 0 to x of f of t dt. So I want you to notice that the function f starts at x equals 0, or in this case t equals 0, and it goes all the way out to t equals 5. So I can plug in an x value of any number in between 0 and 5, and that would simply represent the area under the curve of f from 0 to that number. So let's compute these values. First, we want to find g of 0. Well, g of 0 is the integral from 0 to 0 f of t dt. And this is clearly 0, because if we start at 0 and we end at 0, there is no area to speak of. G of 1 would be the integral from 0 to 1 f of t dt. And this is basically the area from 0 to 1 under the curve f of t. So we are looking at this area. And we can compute this area just by simply knowing the area formula for a triangle. You can see the base of this triangle is 1 unit and its height is 2 units. And we know the area of a triangle is 1/2 times the base times the height. And this is equal to 1. So we know that g of 1 is equal to 1. Next, we want to find g of 2. So g of 2 is, by definition here, the integral from 0 to 2 f of t dt. And now we are finding the area under the curve from here to here. So we're adding a little bit more area. Well, again, we already know this area is the area of the triangle, which we just found to be 1. So all we have to do is add the area of the rectangle here, which is clearly 2 units. You can actually see 2 whole square units there. So the total area under the curve from 0 to 2 is 1 plus 2, which is equal to 3. So we now know that g of 2 is equal to 3. So let's continue and find g of 3. G of 3 is the integral from 0 to 3, which of course we now know is simply the area under the curve from 0 to 3. So here's 3. And I'm going to color this in a slightly different color here. So we are adding this area now. Now again, we already know the area from 0 to 2 is 3. So we're just going to add this area. Now, this area is not precise. You can see that we have slightly less than 1 square unit here. If I shade this in a little bit more, you can see that we have not quite 1 full square there. But then up here we have roughly half of a square. So we would have to estimate these quantities. And I'm going to say that this area right here is approximately 0.8 of a square, and this one here is roughly about half, so I'm going to say 0.5. So in total, the area there would be approximately 1.3 square units. So if I add that to the 3 square units we have here, we get a total of approximately 4.3. And so we know that g of 3 is approximately 4.3. We can't be precise because, again, we don't know the exact value of that area. So now let's compute g of 4. Of course, g of 4 is the integral from 0 to 4, f of t dt. And this is the area under the curve from 0 all the way out to 4. Now, some of that area is now below the x-axis. And I'm going to color this red because area below the x-axis gets counted as a negative area. So again, we already estimated the area from 0 to 3. We had said that that is approximately 4.3 units of area. And now we have to approximate this negative area. Now, if you look carefully, the area down here looks very much the same as the area here. So I'm going to say that this area in here is approximately negative 1.3. So the area from 0 to 4 is 4.3 plus this negative area, which is about negative 1.3. And when you add these together, we're right back at 3 units again. So g of 4, again, we'll say is approximately 3 units. And finally, g of 5 is the area from 0 to 5 under the curve. So it's the definite integral from 0 to 5. And if you look carefully here, all we're doing is adding this little bit of area now. But doesn't this area here look identical to this area here? It does to me. So I'm going to say this is approximately another negative 1.3. So when I take the total area from 0 to 5, I have the area up here, which is about 4.3, plus the area down here, which is about negative 2.6. So we have 4.3 plus the negative area of negative 2.6. And if you put these together, you get 1.7. So g of 5 is approximately 1.7. So the point we're trying to make is that when you define a function to be an integral from a number to a variable, x, let's say, of another function, you are just defining this function to be the area under the curve of this other function. Now let's take a look at the fundamental theorem of calculus, part 1. If f is a continuous function on an interval from a to b, then the function g defined by this integral is continuous and differentiable, and most importantly, g prime of x is equal to f of x. So from our last example, when you define your function g in this way, so g is representing the area under the curve of the function f, it turns out that the derivative of g is equal to f. Or another way I can think about that is g is an antiderivative of f, right? Just think about that last part there. If I say g prime of x is equal to f of x, I can say the derivative of g is f. But I can also say that by saying the antiderivative of f is g. So this function that we define to be the area under the curve of another function turns out to be the antiderivative of that function. So there's a relationship between these two functions. not simply just that G is the area under F, but it's actually the antiderivative. Now, what I'd like to do is give you a very brief idea of the proof behind this, and I will preface this by saying that this is not a rigorous proof, but I want to show you the idea behind the proof. So first, let's consider what the value of g of x plus h would be. According to the definition of g here, it would be the integral from a to x plus h of f of t dt. And then g of x, of course, we already know is the integral from a to x of f of t dt. Now, if you look at the picture, the integral from a to x plus h is the area under the curve from here to here. So I'm going to color that in blue. Okay, so that is this integral. And then the integral from a to x of f of t dt is simply the area from a to x, so just a little bit short of x plus h. And I'm going to color that area green. So if I take a look at the expression g of x plus h minus g of x, this would be the area between x and x plus h. And this is true because I'm simply taking the total area from here to here, which is all of this area, and I'm subtracting off the area from here to here. So this quantity would simply be this area under the curve. Now I'm going to say that this area, g of x plus h minus g of x, can be approximated, let's take a look here, this red area can be approximated by the area of this rectangle. And what is the area of this rectangle? Well, you take the base, which in this case is h, and you multiply it by the height, and the height is f of x. Okay, the height of that rectangle is f of x. So from that, we know that g of x plus h minus g of x is approximately equal to h times f of x. Then I'm just going to divide both sides of this equation by h. And when I do that, I get f of x is approximately equal to g of x plus h minus g of x divided by h. And then I'm simply going to take the limit as h goes to 0 of the left side of that equation, and that should be equal to the limit as h goes to 0 of the right-hand side of the equation. Now on this side, the limit of f of x as h goes to 0 is f of x, and this is because there are no h's in here, so this is essentially a constant. But on the other side, I want you to remember, this is the definition of a derivative, right? The limit as h goes to 0 of g of x plus h minus g of x all divided by h is actually g prime of x. So we can see at least the basic idea here is that you end up getting f of x is the derivative of g, which is what we had said in the beginning, right, up here. So there is a relationship between the area under the curve, f, and the actual function, f. And the relationship is, to get the area, you need to use the antiderivative. Okay, so now let's take a look at another couple of applications of this theorem. So first, we just want to find the derivative of the function g of x defined by this integral. So let's write this down. G of x is equal to the integral from 0 to x of the square root of 1 plus t squared dt. Now, to get g prime of x, I have to take the derivative of g of x. And if I take the derivative of the left side of the equation, I'm going to also take the derivative of the right side of the equation. Now, the derivative of g of x is simply g prime of x. But what is the derivative over here? Well, remember, the fundamental theorem of calculus says that if you define g of x to be the integral from 0 to x of some function, the derivative of that should just be this function, but it's evaluated at x instead of t. So what we get here is the square root of 1 plus x squared, right? So remember the conclusion from the fundamental theorem of calculus. If g of x is equal to the integral from a to x, f of t dt, g prime of x is f of x. So it is basically this function, but with this variable plugged into it. And it's that simple. It's a very simple problem to solve once you know the fundamental theorem of calculus. Now here is a slightly more complicated variation of that problem. So notice here I'm asking you to find the derivative with respect to x of the integral from 1 to x to the fourth of secant of t dt. Now, this would be the same as saying your function g of x is the integral from 1 to x to the fourth of secant of t dt, and then asking you to find g prime of x, okay? This would be the exact same problem, just worded slightly differently. So what we would do is we would take the derivative with respect to x of the left side and the derivative with respect to x of the right side. Now, the derivative on the left side, of course, this is just g prime of x. But then how do you do the derivative on the right-hand side? See, we can't use the theorem exactly because we don't just have x here. We have x to the fourth here. So to do this, what we have to do is make a substitution. I'm going to let u be equal to x to the fourth. And if I do that, this becomes the derivative with respect to x of the integral from 1 to u secant of t dt. But now you can see the variable in the integration here is u instead of x. So when I take the derivative with respect to x, I have to use the chain rule. And the chain rule says you would first take the derivative with respect to u of this thing, and then you have to multiply by the derivative of u with respect to x. So the derivative with respect to u of the integral from 1 to u of secant of t dt, that's just going to be secant of u, right? Just like we did in the last problem. But then I have to multiply by du dx. And if u equals x to the fourth, the derivative of u with respect to x is 4x to the third. So in the end here, I get secant of u, but again, u is x to the fourth, so now I'm going to plug that back in. So that gives us secant of x to the fourth multiplied by 4x cubed. And then the best way to write this as a final answer is to put the 4x cubed in front of the secant function. So how does this work if you want a shortcut explanation of this? If you are taking the derivative of a function defined as an integral, you're basically going to get the function inside the integral. So that's the secant that you see here. However, you have to plug this variable in for t. So we have secant of x to the fourth. But because this is a composition function, you then have to multiply by the derivative of x to the fourth, which is why I have the 4x cubed here. All right, let's go on to part 2. The fundamental theorem of calculus part 2 is by far the more common version of the theorem that we actually use. It states that if f is continuous on the interval from a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of your original function. So in other words, capital F prime is little f. So this says if you have a definite integral, you can find the value of this integral by finding the antiderivative of the function and then simply plugging in the limits of integration and subtracting them. So let's see how this works with example 4. So if I want to find the integral from 0 to 1 of 1 minus 8v to the third plus 16v to the seventh, the first thing I need to do here is find the antiderivative of this function. So let's go through that. The antiderivative of the number 1 is simply the variable of integration. So in this case, it would be v minus the antiderivative of 8v to the third is going to be 8 multiplied by the antiderivative of v to the third. And for that, we can use the power rule, which gives us v to the fourth divided by 4, plus, and then we have 16, and we're going to multiply by the antiderivative of v to the seventh, which is v to the 8 divided by 8. So this is our antiderivative, and I'm going to put it in parentheses here, and I'm going to simplify. And now what we're going to do with this antiderivative is we're going to evaluate it from 0 to 1. And this is how we write that evaluation. We put a vertical line and then 0 and 1. Now remember the conclusion of the fundamental theorem of calculus? Let me write this down very quickly here. It's capital F of b minus capital F of a, where capital F is your antiderivative. Okay? So we have our antiderivative here. Now I just need to plug in the top limit first, and then the bottom limit, and then subtract those quantities. So this becomes 1 minus 2 times 1 to the fourth, plus 2 times 1 to the eighth, minus, then when you plug in 0, you get 0 minus 2 times 0 to the fourth, plus 2 times 0 to the 8. Now 0 to any power is 0, so these all cancel out. And what we end up with here is 1 minus 2 plus 2, which of course is just 1, right? Because 1 to any power is 1. So now we can very easily evaluate a definite integral by simply finding the antiderivative and then plugging in the limits, top limit first, bottom limit second, and subtracting those numbers. One other thought when you do this, when you find the antiderivative, normally what you would do is you would add c. You do not have to add your constant c when you have limits of integration. All right, let's try another one. Here we have the integral from 1 to 9 of the square root of x dx. So when you see an integral, you need to think antiderivative. Okay? Even though technically a definite integral, what it means is the area under a curve. But to find that, you're going to use the antiderivative. So the first thing I'm going to do is rewrite this problem as x to the 1/2 dx. And let's recall that when you take the antiderivative of x to the 1/2, you need to use the power rule, which says you add 1 to the power, and then you divide by that same number, and then you evaluate this from 1 to 9. Now, as soon as I use the power rule to get the antiderivative, the integral sign itself goes away, okay? Because we have already taken that antiderivative. Now we just have to get the value here. So let's simplify. We have x to the 3 halves divided by 3 halves from 1 to 9. And when you divide by a fraction, that's the same as multiplying by the reciprocal of that fraction. And now I just need to plug in the top limit minus and then plug in the bottom limit. Now let's remember how to do fraction exponents. If I have 9 to the 3 halves power, the half power here means the square root of 9, and then the 3 means you're going to cube it. And so this would just be 3 cubed, which is 27, minus, and then 1 to the 3 halves is just the square root of 1 to the third, which of course is just 1, right? So 1 to any power is always 1. So I've got the 27, and the 9 to the 3 halves is 27, but we still need to have the 2/3 there. And then minus 2/3 times 1 to the 3 halves is 1. And then we'll just do the math here. So 2/3 times 27, that's going to be 18, minus 2/3 times 1 is 2/3. And then to subtract these, probably would have been better just to keep the 3 in the denominator there. But we have 54 over 3 minus 2 over 3, which ends up being 52 over 3. This is our exact answer. The next problem is very similar to the previous one. Here we have the integral from 1 to 8, x to the negative 2/3 dx. So the first thing I need to do here is simply take the antiderivative of x to the negative 2/3. And again, we can do this by adding 1 to that power. So x to the negative 2/3 plus 1 divided by negative 2/3 plus 1, and then evaluate it from 1 to 8. Let's simplify. Negative 2/3 plus 1 is 1/3. So we have x to the 1/3 divided by 1/3. And then when you divide by 1/3, that is the same as multiplying by 3. And now I'm just going to plug in 8. So I get 3 times 8 to the 1/3 minus 3 times 1 to the 1/3. Well, 8 to the 1/3 is the cube root of 8. So that is going to be 2. And 1 to the 1/3 is 1. And this ends up being 6 minus 3, which is 3. In our next example, we have the integral from 1 to 3 of 1 over z squared plus 1 over z cubed. So one important point is that if you're going to take an antiderivative, you cannot use the power rule when you have variables in the denominator. So remember, when you take the integral of x to the n dx, this is going to be x to the n plus 1 over n plus 1. Right? This is the antiderivative formula for x to the n. And this is what we call the power rule. And we use it all the time. But I can't do that when the variable is in the bottom. So the first thing I need to do is rewrite 1 over z squared to be z to the negative 2, and then 1 over z cubed to be z to the negative 3, dz. Now I can use the power rule on each one of these. So the antiderivative of z to the negative 2 is z to the negative 2 plus 1 divided by negative 2 plus 1, plus the antiderivative of z to the negative 3 is z to the negative 3 plus 1 divided by negative 3 plus 1. And once we simplify all that, we're going to evaluate it from 1 to 3. So let's simplify. We have z to the negative 1 divided by negative 1 plus z to the negative 2 divided by negative 2 from 1 to 3. Now, z to the negative 1 divided by negative 1. Remember, when you have a negative exponent in the numerator of a fraction, you can drop it to the denominator. And when you drop it to the denominator, it becomes a positive exponent. And then, of course, when I drop that, I still have a 1 on top. So I have 1 divided by negative 1z. And this is the same as negative 1 over z. So all I'm doing there is I'm just going to move that negative to the top and then put the z in the bottom. So this is negative 1 over z. And then likewise, z to the negative 2 divided by negative 2, I can move this to the bottom. So that's going to give us 1 over negative 2z to the positive 2. And then I'm just going to put that negative in front of the fraction. So that's going to become negative 1 over 2z squared. And now we evaluate from 1 to 3. So this is the fundamental theorem of calculus. Now we are going to plug the upper limit in for z into both of these. And then we'll plug in the lower limit. So first, let's plug in 3. Looks like this. Minus, and when I plug in 1 for z, it looks like this. And now let's do the math. This is negative 1/3 minus 1 over 18, right? Because 3 squared is 9 times 2 is 18. And then over here, we have to distribute this negative. So minus 1 divided by 1 is plus 1. And minus 1 divided by 2 times 1 squared is going to be 1/2. And now we just need to combine these together. And you can combine all of them at once, or you can combine them in steps. But I'll just do it all at once. Our common denominator will be 18. What I need to do here is multiply by 6, top and bottom. So this will give us negative 6 over 18. And then we have minus 1 over 18. Plus 1 is like 1 over 1. So I can multiply by 18 over 18. And when I do that, I get 18 over 18. Plus, and then finally here I can multiply by 9 over 9. And that gives us 9 over 18. And now I'm just going to add negative 6, negative 1, positive 18, and positive 9, all over 18. And if we add these up, we get 20 over 18, which simplifies to 10 over 9. In our next example, we have to do a little bit of algebraic simplification before we can find the antiderivative here. So 3u minus 2 multiplied by u plus 1, we can multiply this out before we take the antiderivative. And it's not just that we can do that, we must do that. So 3u times u is 3u squared, 3u times 1 is 3u, negative 2 times u is negative 2u, and negative 2 times 1 is negative 2. And then I'll just do one more step before we find the antiderivative, and that is I can combine those together, and that gives us 3u squared plus u minus 2 du. Okay, now we have a simple polynomial, so we will just use the power rule to take the antiderivative. So 3u to the 2 plus 1 is third power divided by third power. Plus, then we have u to the 1, so that's going to end up being u squared divided by 2 for the antiderivative. And then minus 2 times u, right? The antiderivative of a constant is that constant multiplied by the independent variable here. And then we need to evaluate this from negative 1 to 2. Now, a little bit of simplifying that we can do here is these 3's are going to cancel out. But let's go ahead and plug the 2 into everything. That is going to give us 2 cubed plus 2 squared divided by 2 minus 2 times 2. And then we have negative 1 cubed plus negative 1 squared divided by 2 minus 2 times negative 1. Doing the math, we get 8 plus 4 divided by 2 is 2, minus 2 times 2 is 4, minus negative 1 cubed is negative 1. Negative 1 squared is positive 1, so this becomes positive 1/2. And then negative 2 times negative 1 is positive 2. So here we have 10 minus 4, which is 6, minus, and then here we've got negative 1 plus 2, which is 1, plus 1/2, which is 1.5, which is 3 over 2. And I can rewrite this as 12 over 2 minus 3 over 2, which ends up giving us 9 over 2. So again, the point for this example is that you can't always just find the antiderivative. Sometimes you have to do a little bit of multiplication or simplification before you begin. And you'll get better at this with experience. You won't always know what to do at first when you're first learning this, but with experience, you will get better. Next example is very similar. We have the integral from 0 to 4, 4 minus t times the square root of t. So again, I cannot use the power rule for these because it's multiplied by something else. So the first thing I need to do is multiply this through. Now to do that, let's rewrite this as the integral from 0 to 4, 4 minus t, and then the square root of t, I'm going to write as t to the 1/2. And then I'm going to multiply here. So 4 times t to the 1/2 is 4t to the 1/2, minus, and then we're going to multiply here. And let's keep in mind that this is t to the 1. So when I multiply t to the 1 times t to the 1/2, we know we're supposed to add those exponents, and that gives us t to the 3/2. Now we are ready to take the antiderivative. So here we are going to do 4 times t to the 1/2 plus 1 divided by 1/2 plus 1. Again, just using the power rule. Minus, here we get t to the 3/2 plus 1 divided by 3/2 plus 1. And this is 4t to the 3/2 divided by 3/2 minus t to the 5/2 divided by 5/2. And again, once we're done with this, we will evaluate from 0 to 4, of course. This becomes 2/3 times 4t to the 3/2. So I'm just multiplying by the reciprocal. Same thing here. And one last thing we can do here is 2 times 4 is 8. So that gives us 8/3 t to the 3/2 minus 2/5 t to the 5/2. And again, this is from 0 to 4. So there's a lot of little steps I have to do before I even think about plugging in those numbers. Now let's plug in 4. So we get 8/3 times 4 to the 3/2 minus 2/5 times 4 to the 5/2 minus, and then when you plug in 0, well, when you plug in 0, you're going to get 0 in this case. And this is because 0 to any power is 0. So 8/3 times 0 is 0, and 2/5 times 0 is 0. Next, we have the integral from 1 to 3 of the function y cubed minus 2y squared minus y, all over y squared. And again, this is a very similar problem. The first thing you need to do here is simplify this. You cannot use the power rule, even though you see a bunch of powers. First thing you need to do here is write each of these things in the numerator over y squared. Like so. This is algebraically true. And then we can simplify. Y cubed divided by y squared is y. 2y squared divided by y squared is going to be 2, so that becomes negative 2. And then the last one here, we have y divided by y squared. Let me write that better. It looks like a 4. Y divided by y squared is negative 1 over y with respect to y. Okay, now we can apply the power rule. Integral of y, or the antiderivative of y, is y squared divided by 2. Antiderivative of 2 is 2y. Minus, and then this one here is kind of special. The antiderivative of 1 over y is the natural log of the absolute value of y. And then we evaluate from 1 to 3. Plug in 3. Minus, plug in 1. Let's recognize the natural log of 1 is equal to 0. And this becomes 9 over 2 minus 6 minus the natural log of absolute value of 3 is 3 minus 1 over 2 minus becomes a plus. 2 times 1 is 2. And what we have is 9 over 2 minus 12 over 2 minus 1 over 2 plus 4 over 2 minus the natural log of 3. So I'm just adding up these four numbers, getting a common denominator. And that common denominator is 2. And on top we have 9 minus 12 minus 1 plus 4. And if you do the math there, you get 9 minus 12 is negative 3. Negative 3 minus 1 is negative 4. Plus 4 is 0. So you end up just getting negative natural log of 3. So this is equal to 0. All right, on to the next one. Here we have the integral from 1/2 to 1 over radical 2 of 4 over the square root of 1 minus x squared dx. Now, I can take this 4 and factor it out of the integral. That is a property of integration. We don't always do that, but I'm doing it here because it will help you see what the antiderivative is. So hopefully when you look at this, you understand that that is the derivative of the inverse sine of x. So hopefully you see that just by recognition. And that means that if I'm taking the integral of this, we should just get inverse sine of x, okay? So this is going to be 4 times inverse sine of x, and then we evaluate this from 1/2 to 1 over radical 2. So this becomes 4 times the inverse sine of 1 over radical 2 minus 4 times the inverse sine of 1/2. And I know that inverse trig functions can be a little bit challenging, but when I see the inverse sine of 1 over radical 2, think about a triangle, and think about you have some angle theta, and you know that sine of an angle is the opposite divided by the hypotenuse. So this would have to be 1, and this would be radical 2. And that makes this other side 1 by the Pythagorean theorem. And when you see this triangle, you should recognize that theta here is 45 degrees. And of course, 45 degrees is the same as pi over 4. So this value here is pi over 4. And then don't forget, it's being multiplied by 4. Minus, and then we do the same thing for this one. What is the inverse sine of 1/2? Let's draw a new triangle. Let's say a new angle, let's call it alpha. And you know that sine is opposite over hypotenuse, so it has to be 1 over 2. And this missing side here ends up being radical 3, according to the Pythagorean theorem. And you should recognize this triangle to have an angle of 30 degrees here. So alpha is 30 degrees, which is the same as pi over 6. So this value is pi over 6. And again, that is also multiplied by 4. And so you end up here with pi minus 4 pi over 6, which is the same as 2 pi over 3. And you can subtract and get pi over 3. And in calculus, it's often these kinds of things that you have to do, which cause a lot of struggle. So at any time you need to review algebra or trigonometry, it's definitely worth the time to do it. Next example, integral from 0 to pi over 3, secant theta, tangent theta, d theta. All right, so this one maybe look difficult, but it's not that difficult. And it's because we know that secant of theta, tangent of theta, is the derivative of secant. So the antiderivative of it is just secant. And this just becomes secant of pi over 3 minus secant of 0. And then once again, it's all about knowing what are these values. Well, what is the secant of pi over 3? Well, again, if you think of an angle that is pi over 3, that's a 60-degree angle. The sides of the triangle corresponding to that would look like this. And secant is the hypotenuse divided by the opposite. So it is 2 over 1. And then secant of 0 is 1, because cosine of 0 is 1. And 2 minus 1 is 1. So even though this problem might appear to be difficult, it's not that bad if you know the derivative of secant is secant tangent, right? And then it's also not that bad if you can compute these values. Integral from -1 to 2, e to the x plus 2. This problem isn't bad at all. First thing we need to do is take the antiderivative of e to the x, which of course is just e to the x, plus then the antiderivative of 2 is just 2x, and then evaluate it from -1 to 2. Plug in 2, minus, plug in -1. Do the math. E squared is e squared. 2 times 2 is 4. E to the -1 is 1 over e. And then distribute the negative here. You're going to get positive 2. And so we have e squared minus 1 over e plus 6. And you could leave your answer like this. Sometimes what you will see, though, is that they will combine the answers. So what they'll do here is they will get a common denominator. So what they'll do is they'll multiply by e here, they'll multiply by e here, and what you get is e cubed over e minus 1 over e plus 6e over e. And this is e cubed minus 1 plus 6e all over e. And honestly, they would probably rearrange these terms like so. So this is another way to give the same answer. But again, both of these answers are fine. And now the last example. And this is just to re-emphasize how you find area under a curve. So here it says, find the area under the parabola y equals x squared from 0 to 1. So let's remember that the area under a curve, where you have some function f of x and some limits a to b, if you're looking for this area, it is simply the integral from a to b of the function. So in this case, we're going to have the integral from 0 to 1 of the function x squared. And this is, of course, x cubed over 3. That's the antiderivative. And then the fundamental theorem of calculus says to plug in those limits. And here you just end up getting 1/3. So as an example of the fundamental theorem, this is a rather simple example. So the point here was to remind you that the area under a curve is the definite integral. And that concludes this video lesson.